What I'm going to talk about today and probably tomorrow as well is constructing subfactors with planar algebras. Okay, and since I promised you at the beginning that we were going to talk about a bunch of different diagram algebras, that is the direction we're going today. Okay, so planar algebras don't at first glance fit into the same framework that we've been talking about. So you can, of course, move back and forth. You can make them work, but I'm going to tell you about these the way that I think about them, because then I will be able to tell you some concrete things. Okay, and also don't worry, I'm also going to tell you what a subfactor is, well, at least a little bit. And as to why I'm making this change, having spent a little while talking about tensor categories, the short answer is that I don't know how to do the things that I want to do, which are to construct kind of out of basic objects the planar algebras / tensor categories that I'm interested in. But this is the context I know where you can actually get your hands on these things. Okay, so a subfactor is a pair of von Neumann algebras, and one is contained in the other. That's where sub comes from. And factor means that A and B both have trivial centers. So the only things in A that commute with A are multiples of the identity. Same thing for B. And this is the traditional definition of a subfactor. And then there's this notion that gets called an Australian subfactor. Okay, so this is a Morita equivalence between two rigid, unitary, semi-simple tensor categories with a chosen generator. Okay, a generator of our Morita, the module that realizes our Morita equivalence. Okay.
May I ask why is it called Australian?
It's mostly an accident of geography. The people who say subfactor and mean this tend to, although not exclusively, live in Australia.
Got it. Thank you.
Okay. So why do these two things mean the same thing, really? Okay. So I can certainly tell you how to go from the first one of these to the second one. And moving in the other direction involves some challenging analysis, mostly due to Sorian-Popa, that I'm going to skip over telling you about. But if we are given a subfactor A contained in B, then we can think about B itself as an AB bimodule. Okay? And we could also think of B as a BA bimodule. And the reason for thinking about both of these is that if our indices match up, we can tensor them together. Okay, so we can take X, tensor X bar, tensor X bar, etc., some number of times, or we can do it in the other order, right? We can take X bar and tensor it with X. Okay, and we get, as we do this, a whole bunch of bimodules. And so if we say that C is AA bimodules that are produced as simple objects in one of these tensor powers, and if we say that D is the BB bimodules that we get this way, then we have here two rigid, unitary, semi-simple tensor categories, right? Because you can tensor together an AA bimodule with an AA bimodule. and get another one. And so in addition to these two categories, we also have a module category between them consisting of A, B bimodules. Okay, and so for all of these, when I write down AA bimodules, I don't mean every AA bimodule imaginable. I only mean the ones that appear as a summand of one of these tensor powers. Okay, and so here are your categories, and here's your Merida equivalents. And so subfactors really come with this sort of built-in pair of categories and Merida equivalents. And well, there's more information there than there is if you just have a single category.
Sorry, I think I missed a bit. So X and X bar are just two choices of bimodules, or
B is one of our factors. It's the larger of the two factors. A is the smaller factor.
and so it's naturally a bimodule under. Okay.
Yeah, exactly. So this is a subfactor. And so we take the bigger one and it has an action by itself and it's an action by its subalgebra. Yeah, thank you.
So chosen generator means those appear in these tensor powers, you mean?
Yeah, so the chosen generator here is this,
X. Oh.
is X here. Yeah.
I guess one question is, how do you formalize the notion, like abstractly, of saying, because I see what the chosen generator here is in the setting where it's arising from a traditional subfactor. But if you have the second definition and not have a traditional subfactor involved, what is like the definition of what you mean by, I guess I'm trying to figure out what to think of as generator more generally, if that makes sense.
Well, I mean, of course, given M, some bimodule, we could, you know, take this X thing
Oh, then
and do this procedure and look at its summits.
got it. Okay,
Yeah.
thank you.
You're welcome. Okay. And I've promised that I'm going to tell you about the higher up subfactor. So here is the first concrete thing I'm going to say about the higher up subfactor. That this is a subfactor which has principal graph pair that looks like the following. Okay, so what is a principal graph? So each of these summarizes the structure of, say, this one is our modules, our IB bimodules, and maybe this is the structure you see with M and the category C, and the other one is the structure you see with M and the category D, or even more specifically than that. Okay. The vertices of these graphs correspond to isomorphism classes of simple objects in M or C or D. Okay, and what you should think of is that each of these edges denotes how one of the simples breaks up if you tensor it with X. So the edges here are the fusion rules with X, or X bar as appropriate. Okay, and so what this means is that if Y and Z are appropriate simple objects, meaning one of them is in M, one is in C, or one is in M, one is in D, depending on the tensor we're doing.
So these graphs are naturally bipartite.
Yes, that's right. The number of edges between Y and Z in the graph is the dimension of the Hom space from Y tensor X. Okay, and really what's true is that one of these graphs is for tensor on the right, and one of them is for tensor on the left. One of that's sort of at different stages in here, tensoring by X or X bar makes sense. Okay, so that's why there's sort of multiple graphs here. Okay, but so in these diagrams, we always start with the unit. Okay, so either B as a BB bimodule or A as an AA bimodule. And then we tensor with X or X bar as appropriate. Okay, and so that first simple object is X. And then from that, we can deduce the rest of the fusion rules, or I shouldn't even say that exactly. This contains much of the content of the rest of the fusion rules. Okay, I'm going to come back later to sort of concrete things we can deduce from these particular principal graphs. Okay, but if you hear the word Hager-Graph subfactor, you should imagine these two graphs for now. All right, if you walk away from this talk with only one thing, that's the thing I'd like you to take away. Okay, now as to why we talk about planar algebras when we're talking about subfactors. So this theorem was one of those things that was folklore for a long time, but eventually got written down concretely by Jones and Pennies for the subfactor case, and in the more tensor categorical case by Morrison and Walker, is that if a subfactor, call it A and B, exists, and it has principal graphs, say gamma and gamma prime, then the planar algebra corresponding to the subfactor A and B can be found inside the graph planar algebra of gamma or gamma prime, doesn't matter which. Okay, so in order to explain why this is an important theorem, I have to tell you a little bit about the story of the Hager-Graph subfactor, which is that in the early subfactor days, after Vaughan proved his famous Jones index classification theorem, there was then this question of which indices can be realized. Well, pretty quickly, answer was all of them. And what principal graphs can you have? Okay, and so the principal graph of a subfactor, if you look at its operator norm or its Frobenius-Perron dimension and square that, you get the index. But not every graph can show up as a principal graph of a subfactor. As Dimitri pointed out, it has to be bipartite, but even that's not enough. Plenty of perfectly good bipartite graphs cannot be principal graphs. And so Uffe Hagerup sat down and sort of said, well, what if our index is below 4? It was known that we have one of the ADE Dinkin diagrams as our principal graphs. At index 4, it's an extended Dinkin diagram. More than that, not quite all the Dinkin diagrams are possible, but what about above 4? And so this was the first graph that Hagerup discovered that in terms of its index, I guess I should write that down as the Frobenius-Perron eigenvalue here is 5 plus root 13 over 2. Now that one's the index, so I take the square root. And this is, I don't know, a number that's pretty close to 2. It's above 2, but it's close to 2. Yeah.
Sorry, just one question about the bipartite comment. Why is bipartiteness important? I mean, I can see from the pictures there, I'd assume like so even an odd powers of the generator X.
Yeah.
But
so I have colored chalk today. So basically, because at some of these steps, we're getting an AB bimodule, And at some of them, we're getting, say, a BB bimodule, right? So anything that appears in X or tensor X bar tensor X is an AB bimodule. Whereas something that appears at an even step along the way, X tensor X bar and higher powers, is in this graph an AA bimodule. Okay, and so Howard made this list of graphs that could be principal graphs, that he was unable to find any sort of constraint to rule them out. And so maybe there was a subfactor associated to these. And well, then, of course, the question is, how do you answer that, right? We have procedures that give us subfactors starting from a group or a quantum group. But if we don't have that structure, how do we find a subfactor? Okay, so we're in this more combinatorial world. And so the graph is a really important invariant. Like I said, it summarizes a lot of the fusion data, even if it doesn't quite capture everything. And the answer is this theorem, that if a subfactor exists, then it has this invariant called its planar algebra, very closely related to the categories we wrote down over here. And that planar algebra can be found inside of what we call the graph planar algebra. Okay, so this is just the algebra of loops on the graph at hand. So this is extremely concrete, right? In a way that things that involve the word subfactor usually aren't. It's finite, it's combinatorial, and it's got a lot of structure that means that this is a great place to work. And so what it means is this, that if you want to know if a subfactor exists or not, and you know what its principal graph should be, you have a specific place to start looking. And if you find it, congratulations, you've constructed a new subfactor. And if you don't find it, and in fact, you can prove it's not there, which is a finite problem in this case, then you know that it doesn't exist. So with all that set up, I'm finally going to tell you what a planar algebra is. Okay. When I say planar diagram, I mean something like this, where we have one outer boundary disk and any finite number of inner boundary disks, and they don't overlap. And we have strings connecting them up in any way you like, as long as the strings don't cross. Okay. So what was the data there? We have a single outer piece of our boundary, possibly multiple circles on the inside. We have non-crossing strings whose only endpoints are on the boundaries of circles. And we also have a marked region on each piece of the boundary. Okay, so that's these dots on the pink circles. So one thing we're also allowed to have.
It might be good to make the dots bigger because it's
Are they hard to see? Sure.
a little bit hard to see. I mean, I know what to look for, but.
No, thank you. Yeah. Okay. So the reason that I'm using pink on the outside and white on the inside, I hope that's visible in the back rows, is that some of these things are boundary circles and some of them are just loops of string, right? We said that the loops of string could only, that the bits of string could only have their boundary on the boundaries, but this one has no boundary, so it's fine, right? Okay. And we consider these up to a notion of equivalence of isotopy, but we want to preserve the boundary. Okay. So whatever, a planar diagram is a picture. Okay. The thing that makes planar diagrams interesting is that we can compose them. And we will get an operad from these. Okay. And now I need to see if I can make this work, because what we want to do when we compose diagrams is basically if we can make the outside boundary of one match up with the inside boundary of another, we can pick it up and put it down inside. So we'll do an example. Okay, so I have what, 1, 2, 3, 4, 5. Okay, and so let's draw a picture here that has 5 boundary points. Okay, so what I'm going to do is redraw this picture bigger so that I can pick this up and put it down inside here. Okay, and then the reason that I have these marked points on the boundary is that otherwise it would be ambiguous how I should put this down when I did that. But good question. For this one, it's unambiguous because this one has 5 boundary points and this one has 7. If it is ambiguous, then you need to specify which one you're putting in. Okay, and now we do this, this, and then this is the next one. I've done something wrong already? Yes. Okay, bonus string coming in here. There we go. Great. And then this comes here, and this gets hooked up like this. Okay, and so if I then, this is no longer boundary, right? It's got stuff on the inside and stuff on the outside. So I don't have a boundary component there anymore. And instead I have another planar diagram. Okay, so with this composition, we get an operad. Okay, and so a planar algebra is any family of algebras where we have an action by this operad. So we have a potentially different vector space for every non-negative integer. And we think of the elements of these vector spaces as potential inputs to a planar diagram. Okay, so if a circle has 6 strings coming out of it, that means we should take something from the space V6 as our input there. Okay, so a family of vector spaces, an action of the planar operad. So that, for example, okay, not that this is a particularly important diagram in any sense, but so what do I have here? I have a boundary component with 3 strings coming into it. That means I should take something from the vector space V3. My next of these also has, let's erase that one. Okay, now it has 2 strings coming into it. So that input should come from V2. And for this inner disk, we have 4 strings coming out. So that should come from V4. And the data of the action of the planar operad is how to interpret, how to get a multilinear map with target V5 from this picture. Or more generally, a recipe to turn any picture into a multilinear map. Okay, and of course, what makes that challenging is that we want to do this in a way that's compatible with the operad structure. So compatible with composition. Okay, so we have an example of composition written down already. Let's make use of this. So what's going on here? Well, we have inputs coming from V6, and there are, I think, 7 strings around this disk. And our outside has 1, 2, 3, 4, 5 boundary points. And here we have inputs coming from V4 and V5 and V3. And they're giving us an output in V5. Right? I hope that I've counted those correctly. 6, 6, thank you. Okay. Yes, that's much better, because what we want is that if we start with V4, tensor V5, tensor V3, and we go to V6, and then using this diagram, and then we use this diagram to go from that copy of V6, tensor V7. So, okay, if I want to write down a coherent diagram, I should tensor with V7, right? And then we get a map to V5. And if we do it in 2 steps here, we should get the same thing as if we just did this whole thing all at once, which has 4 interior disks and still lands us in V5. And so that's a definition. Do such things exist? Of course they do. I wouldn't tell you this if they didn't exist. So, but the first example is maybe not all that interesting, but it's something we've already seen this week. Okay, the temporally Lieb algebra is in fact the temporally Lieb planar algebra, right? So TLN was the span of these TLN diagrams between endpoints on a line and endpoints on a line below, right? And any diagram we can draw with non-crossing strings in the middle is a temporally Lieb diagram. And of course, these are good inputs to something like this. It's pretty easy to see that if you had a temporally Lieb diagram and, okay, well, I guess these are rectangular and these are circles. So I should specify that if we have something like this, we turn it into connections among 2 endpoints on a circle by putting the marked region down at the left-hand side here. Okay, so this picture becomes what? Okay, still just a non-crossing pairing of 2 endpoints. And so if we had a bunch of those pairings and we put them down inside some particular planar diagram, what we would end up with is, again, data about a pairing of the points on the outside. Okay, plus also possibly some loose strings floating around, but we know how to deal with those in temporally Lieb, right? We throw them out and we multiply by delta. So, cool. Okay, that's maybe not the most edifying example, because the real question is how you would take something that doesn't seem to be innately diagrammatic, like literally built of diagrams, and interpret these sort of pictures. And of course, the answer is that the same things that we were seeing earlier this week, the same ingredients, a cup and a cap, horizontal composition, vertical composition. If we have some sort of algebraic object where we can make sense of those, then we can make sense of planar diagrams. Okay. And so with no details, I'd like to talk about the subfactor example. So let's say we have one of these categories. I guess I've erased them by now. Bimodules for A contained in B. Okay. Now, remember this was generated by, we abbreviate B as an AB bimodule by X. Okay. And now, in this context, we really do have a need to keep track of orientation, except in this case, I'm going to call it shading. Okay, so I'm going to have some unshaded regions and some shaded regions, and the convention that the shaded regions correspond to B and the unshaded regions correspond to A. So when I have a string like this, I'm thinking of it as labeled by X. And then the things we'd like to make sense of are the sort of fundamental planar diagrams. Okay, so it's maybe not very surprising theorem that any planar diagram can be built up from being able to interpret the cup and the cap, and those should be, I don't love this, but okay. And the operation of just setting two things down next to each other in an unconnected way. Okay, so this is sort of boring, right? You could take whatever diagram you have and arrange it nicely so that whenever the strings meet one of these boundaries, they don't do so at a minimum or maximum. And when the strings do have local minimums or maximums, we can interpret those using the cups and the caps. Okay, so basically, to build up to any picture like this, we'd start by putting some things down in an unconnected way, and we would connect them and move the strings around by using cups and caps. Okay, and so if we can understand these, that gets us everything.
So the reason why you have like two cups and two caps is like going across them or staying by itself? Or...
That's because I should be drawing in the shadings here. Okay, so unlike yesterday, we do have something that we really need to keep track of the orientation, and we're doing it using shadings now for historical reasons.
For the two things that are we assuming that the marked region is on the left now, right? Is that...
Good point. Yeah, we need marked points, and really maybe it would be better to, it doesn't really matter, right? So let's just have all the strings going up. So we just put these down next to each other, and we don't let the strings interact at all.
And do we have these? So I guess is one of them those things supposed to be the exterior region is shaded, and one of them the exterior region isn't shaded? Or
yeah, no, that's true. That really, I shouldn't drop the exterior of this diagram, and we should consider the possibility. Yeah, there's really two versions of these. These points are in unshaded regions, and one where they're in shaded regions.
I guess I have a quick question: is why do we need them to be like juxtaposed? Why don't we have just like built out of like single things? Because like you can just like move them slightly so they're not right next to each other, right? You draw them. I guess I don't know if it makes sense. The question I'm asking.
I mean, what I'm getting at is, if we're going to build up planar diagrams, we need to be able to have more than one input, or maybe more than zero inputs, right? All of these things so far, in fact, have zero of these input disks.
All right. Cool.
Okay, right. So, okay, but what I wanted to say was that this is where we actually use the subfactor structure. So, what is this map supposed to be? This is supposed to take X tensor X bar and produce the unshaded unit object, which is going to be A as an AA bimodule. Okay, so this map takes, we have B as an AB bimodule, and then we have B as a BA bimodule. And we tensor them over B, and we want to map to A, right? So this tensor product is just B itself, and the map from B to A is called the conditional expectation. Okay, so it's a feature of subfactors that we have such a map. And now,
is that somehow the unitarity? Does it have a company?
I don't know. Okay, and what about this one? This does the tensor product in the other order. We have B as a BA bimodule, and we're taking the tensor over A, And now we're landing in B. Aha, this is multiplication, right? Okay, good. This is one of the easy ones. What about this picture? In this picture, we want to start in A and end in B, tensored with B over B. So in other words, just another copy of B. So this is the inclusion map. And then the last one of these is going to take B into B tensored over A with B. And this is Jones's basic construction. All right. And then this and its analogs are just tensor product of modules, right? Literally putting things down next to each other is the tensor. Okay. And so this is really the same story we've been telling all week, right? Ways to interpret diagram algebras just by knowing what these particular pieces do. All right. And so the last thing I'm going to do is give you one more example of a planar algebra. And this is the graph planar algebra in this theorem. Okay. All right. And this is one where you really do get to see the planar diagrams acting in an interesting way, I feel. You have sort of more combinatorial data, and you have a more holistic approach to your planar diagrams. Okay, so G is a connected graph, and you don't actually need to assume that it's bipartite, but if it all of the ones we care about from subfactors are bipartite by necessity. So the graph planar algebra of G has to be this whole family of vector spaces. And so the kth one of these is the set of functionals that take in based loops on G of length K and produce a number. Okay, so this is just, dual to the vector space of all the loops you can walk on this path. Okay, a really tiny subexample. Let's take a moderately sized graph, not too big, and we'll name its vertices A, B, C, D, and E. What is GPA 0? What is a length 0 loop on a graph?
You stay with the same vertex.
You stay on the same vertex, yeah. So the length of these loops is the number of edges they traverse through. We traverse through 0 edges. And so this is just functionals from any of our 5 vertices. Okay, so, oops. Good. What about something more interesting? What about loops of length 2? So these correspond to functionals from the edges of the graph to C, right? Really, you do an edge and then you do its reverse, but that's what this amounts to. Okay, and so forth. So how do we make sense? How do we get planar diagrams to act on these graphs?
Excuse me, it's the function of oriented edges.
Yes, that's right. So when I draw this, I really mean that there's an edge in both directions if I haven't specified the orientation. Yeah. Okay, so we want an action by planar diagrams. So if our planar diagram is called P, then I define a G state on P to be a way of assigning vertices to regions and edges to strings consistently. So vertices get assigned to regions, edges get assigned to, and so if two regions share an edge, then the edge assigned to, if two regions share a string, then the edge assigned to that string should connect the vertices assigned to those regions. So, for example, do something small here. Okay. And let's say we're still working on the graph from that example. Okay, and so we just start writing down labels of vertices in regions. Okay, so we can have A and we can have B and we can have C. And now we're sort of constrained, right? Because whatever vertex goes here must connect to C by an edge and must connect to A by an edge. And so there's only the choice of B here. But now for this region over here, we could take any of the vertices that connect to D to C. We could take B or D or E. So we just make a choice. Okay, so this is a state on the planar diagram. Because we had a simply laced graph, I didn't label the edges, but if our graph had more complexity, of course, we should keep track of not just the vertices, but which edge gets assigned to each string. Okay, and now if we have, say, a state sigma, and we read around one of the boundary circles, what we get is a loop on our graph, right? So over here, with this boundary circle, we get the loop A, B, C, B, A. And with the outside, we get A, B, C, E, C, B, A. And so what that means is that these functionals on loops make sense to use as inputs inside these boundary regions and will produce a functional themselves. So I will write this down. The full definition maybe isn't much clearer than what I just said, but let's be careful. Can I fit it on this board? I'm not using my boards very well. Okay. So P, a planar diagram, acts on functionals F1, F2 through Fi in the following way. P of these inputs should again be a functional. And so let me give it, therefore, a loop L on my graph of the correct size. Now, what is this to be equal to? I want to look at all states on my graph, sorry, on my planar diagram, state sigma on P, such that sigma, when I read around the outside boundary circle, back the loop L. Okay? And now, for every state like that, I take the product over all of the interior boundary circles. Say this goes from F1 through Fk, so there are k of these, of Fi acting on what I get when I read the state sigma off on the ith inner boundary circle. Right? So these state sigma produce loops if you read around any of these boundary circles. And so I evaluate my functionals on the loops we get. And if it produces this loop, then it makes a contribution. we should do at least one example of this because it is harder to write down in technical detail than it is to actually work with, in my opinion.
The planar diagram in your example is not the one that corresponds to the graph that you gave up there, the ABCD graph, is it? Because it doesn't seem to have the same adjacencies.
I think it's okay, right? A connects to B, B connects to A and
There's
C,
no D.
C connects to E. So that's right. It is a possible state
Okay.
that's compatible with this graph. There are many, many possible states that are compatible with this graph. It is just one of them.
Okay.
Well, in fact, let's go ahead maybe and interpret that particular diagram without the states and see what it gives us, okay? Okay, so what do we have? We have this, and now, okay, we're still working with that same graph G. And let's pick a particular input F here, okay? Let's say that F is the functional that gives me 1 if my path goes from A to C and then back to A. So it's A, B, C, B, back to A, and 0 otherwise. Okay, and so now, according to this definition, if we want to know what this does on any particular loop, we have to sum over states that are compatible with that loop. Okay, so let's look at this and say, what does this do to the path that goes A, B, C, and then to E, and then back to A along the same path, C, B. Okay, and so this loop tells me what the sort of outside of my region should be labeled as, right? A, B, C, E, C, B. And in fact, for this particular diagram, once we've labeled the outside, there's no choice, there's no freedom left, right? So there's only a single state that's compatible with this loop, and we've just written it down exactly. And so then we look at the product over all the inside circles, but there's only one of them, of what F does to the path we get from reading along this boundary, which in this case is A, B, C, B. It happens to be 1. Okay, and so what else could we plug in here to get something non-zero? We could have used the path that goes from A to D and back again, right? And the only change with that is that then we'd be labeling this region with a D, but we would still, in fact, get the same thing here, and so we'd get 1 back. Okay, so on the other hand, what if we gave this something different? Okay, let's give it something truly different. Let's take the path C, B, C, E, C, D. So this is a path that starts at C and goes out to every vertex that's 1 edge away before coming back. And so now we would want to assign C to this region, B here, C here, E here, C here, and D. And so in fact, we've labeled the regions consistently still, so we're okay, but we would read around the inside here, and we'd see that we have C, B, C, D, which the particular F we've picked gives us 0. Okay, and the one other way that we could get a 0 here, let me see if I can pick a path that does this. How about C, B, nope. B, I'm going to write it down around the outside. See if I can make it work. B, C, D, C, E, C. Okay, B, C, D, C, E, C. Well, now we're taking an empty sum because there's no state here which is compatible with this data on the outside, right? Whatever label on this region, it can be either D or E, but not both. And so this one gives us back 0, as does every other loop on this path, on this graph, except for these two. Okay, so those state sums are how we actually compute the action
I
of
feel like
the
there might
planar
be one
tangle.
other that gives it if you do A, B, C, B, C, B.
Okay, thank you. Sure. A, B, C. I have an E and a D. We could also go back to C. Yep, this one should give you 1 also. Okay. And so that state sum definition is how the planar tangle acts on functionals on this graph. And come back tomorrow and I will tell you about using this graph planar algebra to do more exciting calculations.
Any questions or comments? Okay, let's thank Emily again. Oh, I'm sorry. Go ahead.
Ask Emily if you could explain again why we're labeling the edges of the circle instead of the regions interior to the circle.
Sure. So the idea is that we're trying to find states that label the regions in a way that's consistent with reading this out around the edge.
So in this case,
So,
you can't.
in this
That's the
case,
thing, because you put a D and an E for some reason.
well, exactly, that if I tried to give this loop as an input and find states that are compatible with that, there are no states that have that property.
Okay.
So,
Other questions or comments? Let's thank Emily again.